EEE 145, Chapter 2, per unit systems. So what is a per unit system? A per unit system is a percentage of a given base value. Okay. One way you could think about it is we draw it as like a decimal place, like 0.8 per unit. This is pretty much equal to 80%. It's a percentage at the end of the day of a base value. Okay. Per unit pretty much stands percentage unit. Now, on the side, somebody will ask, well, why are we talking about this? The power system uses per unit extensively all the time. So it's something we started using maybe 100 years ago, and we kind of adopted it. So you're gonna have to know it, right? Most other electronics disciplines or electrical disciplines don't use it. It's mainly just power. Okay. So we said a per unit value is a percentage of a base value. Well, then the next question is, what is a base value? A base value, let's write it down, is a value like voltage, current, or whatnot we design / chose, right? So basically, in the design side of engineering, whenever we're building a substation, transmission lines, we'll pick a certain level of voltage and MVA and current that we expect to happen, and that's the base value. Okay. Now, an actual value is a measured value, is measured from the field, measured from the field. Okay. This is what is physically there. Physically there. Now, the actual value can be different from the base value because the base value is the ideal expected circumstance. But in reality, we could go plus or minus 5% or something. You know, there could be deviations, right? And it's very important to try to see these deviations and note them, okay? So how can we define this percent value? Right? Well, any quantity, be voltage, current, in a per unit system is an actual value divided by the base value. So for example, if I expect my substation to run at 230 kV, right? It's a standard high voltage standard you'll see in California. But in reality, it's a hot summer day, and we might be running 200 kV. So we're 30 kV short, right? Now, is 30 kV a lot? Well, it depends where you're at, right? Probably, but if you're running at 1,000,000 volts, 30 kV is not that much. So instead of looking at hard numbers, why don't we put it in a percentage? So then we could gauge, is being down 30K really terrible, or, you know, can be tolerated? Well, if you take your calculator and 200 divided by 230, right, it's going to be 87%. So we could write 87 per unit, or we could multiply by 100 to then get 87%, right? So decimal and the percentage is just off by 2 decimal places, okay? And this is 87% of rated value. Another way to say this is 200 kV is 87% of 230. So what I can see here is, hey, we're down 13%. That causes some alarm. Typically voltage, you don't want to see it go below 5%. Definitely under 10%, you're going to have some people going to start calling. 87%, your system is still live, but we're probably going to have to fix it, right? This is a comparison. If this was like 20 or 30%, your system is already collapsed by then, okay? So in my opinion, or in most of Power Engineering Society, percentage is much better than hard numbers. because we said there's a 30K difference here, right? So let's write 30 kV difference, right? So that's your difference. Let's compare it to another quick example down here, right? Let's say we had the same 230 kV line. We're running at 240 kV this time, right? So we're actually a little high. We're a little hot. So our per unit, again, is actual value. Ugh, let me write that. Purple. Actual value divided by the base value. Okay. Now, again, we're running a little hot, so we're 240 kV over 230. Now, again, is that an alarm? Is that crazy? Like, oh, this is 10 kV high. So that's a 10 kV difference. Now, some people say, oh, 10,000 volts, that's enough, that, you know, that's disaster waiting to happen. Is it? Well, we really got to look at a percentage. So if we do 240 divided by 230, this is actually 1.04 per unit. Or we could convert it to 104%. So the way I read this is only, we are 4% above rated value. Okay. And actually 4% is perfectly fine. IEEE defines that maybe plus or minus 5% from the rated value is okay in the power system. So yeah, 10 kV, oh, I'm scared because that's a lot of voltage, but in reality, it's only 4%. That's actually normal day-to-day activity, right? So this is one big advantage of per unit system is percentages are easier to dictate than hard numbers, right? Okay, so let's keep on going. Now we kind of have the idea of what percentages mean in the power systems, right? High percent, small percent, okay, big percent, kind of dangerous, right? Now let's start talking about in the power systems, where do we use per units? Well, the typical measurements we get in per units are voltages, right? Voltages are pretty important because that shows you how healthy your power system is. Power is very important because it shows how much you're transferring power from generation to loads. Current is very important because that shows you how much current is flowing through the line so you don't overheat them. And then impedance is important because you need eventually calculate your losses. Now, notice one thing, we don't have frequency here. We typically don't use per unit for frequency, right? Because frequency tends to be stable at 60 hertz. We don't have big variations of frequency. But these voltages, power, current, impedances, they can go all over the place depending on what part of your power system you're looking at, right? If you're looking at a transmission system versus just a generation system, your voltages might be 10 times higher, right? So then your current can be 10 times lower and your impedances is going to be all over the place, okay? So how does a per unit system make our lives better? How does it help compare voltage across systems? Kind of just mentioned that, but we'll say again. Power system has many voltage levels. Let me redraw that A. Might confuse some people. Levels, right? We could go all the way down from like 12.47 kV, all right, all the way to 768 kV, which is extremely high, right? That's almost 1,000,000 volts, okay? Using a percentage, kind of what we talked about previous slide, use a percentage can identify large voltage swings. Okay. Again, large voltage swings, lots of percentages off. That's a danger mode that your power system is becoming unstable and going offline. Okay. How does it help make transformers simpler to analyze? This is the beauty of it. You actually straight up ignore the turns ratio completely. Right? Remember, transformers have a like 5-to-1, 10-to-1 turns ratio, that N1 over N2 shenanigans. We pretty much ignore it completely. Ignore the turns ratio completely. And the reason why is when we're using percentages off of on a transformer, instead of saying hard, I'm 10 kV versus 100,000 volt. Sorry, if we compare 10 kV to 100 kV, right? We know we have to multiply by 10, but we could do percentage on both sides and then they'll be equal, right? We'll talk about it in a second. It might be confusing a little bit there. Okay, so how does it help us simplify three-phase versus single phase and line-to-line versus line-to-neutral, right? Because remember, they're different, right? You might have VAB versus VAN, right? Remember, there's square root 3 difference, right? 1.0 per unit means 100% of any voltage, okay? So if I say 1.0 per unit of VAB is equal to, it means the same thing as 1.0 per unit of VAN, right? Because there's always a percentage. So percentage is like normalizing a number, so you don't have to worry about the hard number. Just say I'm 5% above or 5% below, okay? So in a power system, if you see a 1.0 per unit VAB, at that same point, the VAN will also be 1.0. They're not going to change, okay? Lastly, how does it help us integrate equipment with nameplate values? Well, whether you like it or not, nameplate data. So nameplate data, this is the specs of the equipment from the manufacturers, right, is given. That's a funky looking S. Is given in per units, right, from the maker. Right. So again, the power system has standardized. We're going to use per units across the board. So every equipment you're going to buy is going to have some per unit values. You're going to have to adopt this system. Okay. All right. So we kind of hopefully painted a good broad picture of the per unit system, at least in English. Right. Now let's start going in more detail. Okay. Let's start defining individual quantities. Okay, the base quantities are the starting point. How do we figure them out? So again, from the design engineer, or maybe you inherited something that you didn't design, or the person who designed it's already gone. You just look at equipment specs, right? So either you personally designed a system and then you chose your base values, or something else chose it for you and you just have to go with it, okay? Now, if you have to choose your own values, you typically want to choose a base value that closely fits your system. Okay? Meaning you could technically choose any voltage, any current, any base, any power as your starting point. But to make your life easier, you want to choose these values that are already in your power system. If your whole power grid runs off 115 kV, then you should choose 115 kV as a starting point. Okay. So what are the four major quantities we look at in the per unit system? We're always going to look at voltages in per unit. We're going to look at current in per units. Sometimes we'll look at power, sometimes we won't, depends. And then lastly, impedances are always in per unit. Okay. I'm going to draw a little star on impedances because impedances are almost exclusively in per unit, so you can't get away from it. Voltage, currents, and power, if it's a very small system, they might not use it. If it's a large system, they're going to probably adopt it. Okay. Now, notice overall we have four quantities. So we need to somehow figure out these hard quantities, right? Because we have four things, we have to choose a starting point. So typically, power base is the starting point. So we choose a power base is chosen first. Okay. Okay. Now, most of the world chooses 100 MVA as your starting point. That's just 100 is a round number we all like. Most power systems are in the hundreds of MVA. And so almost every power grid, our power base is 100 MVA. So just pretty much get used to that number. Okay. Next, after a power base is chosen, we choose voltage bases. Voltage bases. Okay. Again, remember, bases are the starting numbers we're gonna base our percentage off of. Now, what's the rule for this? So you choose the voltage bases and then choose them. Well, I already say choose. So we'll select a voltage base for every level, every voltage level in your system. Okay. If you have only one voltage level, like 115 kV and nothing else, you just choose one voltage base. If you have a 115 kV and maybe a 69 kV system, so if you have a 115 kV transmission grid, you might have a sub transmission grid of 69 kV. Both of these will be your bases. Okay. And you can even say if your distribution, you might have 12.47 kV, you could add that into your base values as well. So it depends how big your power grid. If your power grid is really big, you might have 10 of these. If it's really small, you might only have one. Okay. Now notice we have power and voltage. We need two more. We need current and impedance. Right. So current base and impedance base, their bases, because you can have more than one, are calculated from the voltage and power base. Okay. And we could just use basic Ohm's law and P equals VI, that type of stuff, right? So in the end, when you start a per unit system, power is the first thing you choose, voltage is the second thing you choose, and the current and impedances are calculated afterwards. I will say, when you're starting a system new, it's a lot of work to choose your bases and get the system set up. But once you have the system set up, just maintaining it and using it on an everyday basis is a lot easier. Now, most likely, the power company you're going to go to already has the base value chosen for you. You're just going to get sucked into the system and use it. But for some reason, if you go and you're building a new power plant, you're building a new refinery one day, you're going to have to choose these base values. Okay. So we did a lot of talking. Let's do some numbering. Right. So here we're going to start defining how do you do the calculations. So remember, we said base power in kVA is what we start with. So we have three-phase power. So kVA is, remember, apparent power. Okay. This is that S value. Okay. So it's apparent power S in kVA. Or you could do MVA, depends how big your system, megavolt amperes to kilovolt amperes. Okay. Next, we have voltage. This is going to be your line-to-line voltage. Okay, remember, in the power system, almost everything is based on line-to-line. Very rarely do we do line to neutral, so you'll have kV line-to-line. Okay. And that's in kilovolts. We typically don't use megavolts, and we don't use just regular volts. So kilovolt is typically a standard you'll see. All right. Now that we have our voltage and power, we could calculate our current. Now, this is a formula you're going to pretty much see for the rest of your life. Current is your three-phase. I'm going to write three-phase right here to remind you. Your three-phase power, right, kVA, divided by square root of 3 times your voltage, kV, line to line. Okay, just get used to this. Okay, so again, I'm going to repeat three-phase apparent power on top divided by square root of 3 times your line to line voltage. Okay. Next, how do you figure your base impedance? This is going to be your kV squared, right, over your MVA. Okay, so this time let's use MVA instead of kVA. Now, one way to check is you can ask yourself, you know, if I'm doing this formula right, this whole thing should be amps at the end. So if we look, we have voltage right here. So if we really want, we could cross out the voltage here. We could cross out the voltage here. We're left with amps. That makes sense to me. Okay, this old physics trick. Write down your units. At the end over here, we want Z. Remember, V equals I times R. Okay, if I want R, it's going to be V over I. So I just need to make sure at the end, I have volts over amps. That's going to be equal to ohms. So again, we have V squared over VA. So if we cancel a V here and cancel 1 over V over there, we're left with a voltage because the voltage is squared. So, you know, squared means 2 voltage times voltage. So one voltage is canceled, another one's canceled. So we have volts amperes in the end, which is ohms. Okay, so just really quick, let's check the units. Everything works out. Okay, so these are the 2 major formulas you're going to see over and over again whenever you're doing base quantities and per unit systems. Okay, so like usual, let's kind of do a quick example to see how it goes. Now, this is one of those, we're going to take a break for about 15 or 20 minutes. We'll let you do the work. I'm going to start it out real quick just to, you know, that way you're not 100% confused. So here there's a generator on the left-hand side, 100 MVA, 12.5 kV. Z percent is 0.05 per unit. So that's the impedance of the generator. There's a low voltage bus at 12.5 kV. There's a transformer linking a high voltage bus at 25 kV that goes to the load. Notice the transformer is 100 MVA, 12.5 kV on the low side, 25 kV on the high side, and the impedance of the transformer is 0.1 per unit, or 10%. So remember, we want to select the optimal base values first. So select your kV and your MVA. Okay, so for MVA, I'm just going to tell you, let's do 100. Okay, again, that's what everybody uses. So I would say let's start with 100 MVA. kV, notice there's 2 columns because we have 2 voltage levels. We have 12.5 kV, 25 kV. So I'm going to write 12.5 kV here. And then I'll let you choose the other voltage and then figure out your current base and your Z base based on the 2 formulas from above. Okay, so let's take a 15-20 minute break, get your calculator out, number crunchies, and we'll come back and we'll check your answers and we'll keep on going. Okay, so see you guys in a second. Okay, welcome back. Here we're going to keep going with the base quantity examples we're talking about before the break. So here, remember we chose 100 MVA, 12.5 kV base, but remember there's another voltage level. There's 2 types of voltage levels, so we're going to do a second one, 25 kV system. Okay. Now, one thing to note here is this 12.5 kV, you could kind of draw a column like this. And now your I base and Z base are all going to be based on this 12 kV system or 12.5 kV system. So anything on bus 1, on the generator side, on the 12.5 kV side, a transformer, we're going to use I and Z base there. So let's go ahead and calculate our I base. So I base, remember, is 3-phase power. So it's going to be 100 MVA on top divided by square root of 3 times our kV line to line, which is 12.5 kV. Okay, we're going to go ahead and number crunch this. And this will be 4.62 kiloamps. So here I will put 4.62 kiloamps. Okay. Next, we could do our Z base. So Z base will be kV squared. So in our case, is 12.5 kV. Square it. Okay. Divide by our 3-phase power, which is 100 MVA. Okay, this Z base will be 1.56 ohms. Okay, so we're going to write 1.56 ohms. So now, anytime you're on 12.5 kV side, if you figure out your current per unit or you have an impedance like the Z percent 0.05, you can actually find your hard impedances or your actual regular current based on this kind of, I call it a Rosetta Stone, right? Because it keeps track of all your base values per your system level. So now we did one, we could do the other side, which would be here, our 25 kV side. Okay. If I wanted to, I would draw a line down here and I would go ahead and calculate my I base for the 25 kV side. Okay. Now the only difference is you would say 100 MVA divided by square root of 3. And this time we're going to multiply by 25 kV or divide by 25 kV. Okay. Number crunching that, this is going to be 2.31 kiloamps. All right. And then lastly, for our Z base, again, we're on the 25 kV side. So it's going to be 25 kV squared divided by 100 MVA, which then would be 6.25 ohms. Okay. All right. So again, notice that we kind of drew a little couple columns where we have a voltage zone of 12.5 kV and a voltage zone of 25 kV. And those two columns are your two base values. Notice that the I base and Z base are different per kV zone. Next thing notice is 100 MVA is across all of the voltages because again, the 100 MVA is based on your entire system, not per zone. Okay, so again, MVA is the entire power grid, and then kV bases, I base, and Z bases are per voltage zones. And in this case, we only have two. Okay. Now, this is what I call the Rosetta Stone. So anytime we're going to do some calculations, this is the base values we're going to refer to whenever we want to try to find the actual ohms and actual amps or actual voltages away from the per unit system. Okay, again, Rosetta Stones is if you want to go from a per unit system back to just regular volts, amps, and currents, and volts, amps, and ohms, you have to use this table. If you have volts, amps, and ohms, you want to go to per unit, again, you're going to have to use this table as a conversion factor. Okay. Now, let's go ahead and start kind of seeing these have in practice. So first thing I want to do is let's look at this transformer, right? I just pulled the straight transformer from the previous page, and then let's see, well, how does the transformer act with per units involved? So if we have a per unit system, how can we make the voltage calculations easier? Remember I said before, we can ignore the turns ratio. You remember for a transformer, voltage turns ratio is V1 over V2 is N1 over N2. This is a ratio of finding out the voltages across the transformer. Okay. Now, if we have a 25 kV system and then, or sorry, 12.5 kV to a 25 kV transformer rated at 100 MVA with a Z%, 10%, what is the voltage if I calculate a 0.97 per unit on the low voltage side? Well, my actual voltage level in volts is always going to be my per unit value measured multiplied by my base value. Okay. Now, per unit, we calculate 0.97 per unit, right? What's my base value? Well, we're in the low voltage side. This is my base value right here. Okay, this is the 12.5 kV section of your grid. So you're going to multiply by 12.5 kV. So your resulting number will be 12.13 kV. That's my actual voltage in volts, not per unit. Okay. Now let's do the same thing on the 25 kV side. So let's say we measure 0.97 per unit on the 12 kV side. Okay, so this is 0.97 per unit. The other side was also 0.97 per unit. Okay. So let's then do the same thing. Actual value is equal to a per unit times our base value. This is going to be 0.97 per unit times this time 25 kV because we're on the 25 kV side. This number is going to be 24.25 kV rounded. Okay. Now you can see one big advantage of using previous system is the per unit voltage is the same across per the transformer. So per unit voltage is the same across the transformer. Now I'm going to say a lossless transformer. If realistically, if you have some losses, you might have a very tiny voltage drop, but to make things simple, we'll say lossless transformer. Okay. It's much easier for me to say, oh, well, I know my voltage is 0.97 per unit. I'm just going to hop over to transformer and keep my 0.97 per unit and keep on going. If we were in regular volts, I would come up on one side and say, well, I measured 12.13 kV. What's my voltage on the other side? Well, I need to go V1 over V2 and 1 over 2. It's an extra formula and an extra step to calculate 24.25 kV, right? When in the end of the day, they're both 97% of rated voltage on both side transformers. So if you stay in a per unit system, you could straight up ignore the turns ratio because of per unit voltage goes straight across it and it doesn't change. Okay. Let's do the same thing and ask ourselves, well, what about the current? Right? We have current flowing through a transformer. Can we make our lives easier? Yes, we could again ignore the turns ratio. Okay, I keep harping on this because this is a big deal. Right? Again, what's the current across the transformer? It's I1 over I2 is equal to N2 over N1. Did you remember to invert the 2 and a 1? A lot of people don't. Again, extra turns ratio formulas confuse people and it's just more work. Okay, so let's say we have 0.7 per unit current flowing through a transformer. That means the current is flowing into the transformer at 0.7 per unit. Okay, what's my current on the 12.5 kV side? Okay, so again, 12.5 kV side, 12.5 kV side. Can I figure out my actual current in amps? So the actual current flowing, again, is your per unit times your base value. Okay. In this case, our per unit value is 0.7 per unit current multiplied by our base value. What's our base value? Oh, we need the Rosetta Stone. So notice we're on the 12.5 kV side. We got to scroll up, look at our little chart. 12.5 kV side, 4.62 kiloamps. That is our base value. So we're going to go back over here and bring it with us. Okay, so let's write, I'm going to change color. Just remember 4.62 kiloamps. Okay. So what is this going to equal to? Well, let's number crunch it. This is 3.23 kiloamps. Okay. Now we could do the same thing on the other side. Let's call this green. Let's do 25 kV. So let's do I actual is equal to, again, per unit times the base value. Right, but now we're looking at the bus 2 leaving the 12 kV side. So we're looking on 25 kV side. We're looking at the current going out. Again, it's still 0.7 per unit. Remember, the current that goes into this transformer, the percentage is the same as going out. Why? Because we ignored the turns ratio. So 0.7 per unit current going in is equal to 0.7 per unit going out. Now, if we want to calculate our actual amperage, it's again 0.7 per unit multiplied by base value. What's our base value? We're in the 25 kV side. We're going to have to go up there to Rosetta Stone and look at it again. All right, so 25 kV side, we're looking at our I base. We're looking at 2.31 kV in green. So let's bring it back down over here. 2.31. I wrote that kind of funky. 2.31 kiloamps. So let's number crunch that. That's 1.62 kiloamps. Okay, so as you see, if we're using regular current, on one side transformer, we'd have to remember 3.23 kiloamps. We have to go through our turns ratio N2 and N1 to get 1.62 kiloamps. I don't want to do that extra turns ratio calculations. I just want to say 0.7 per unit goes in, 0.7 per unit goes out. It's way easier. Again, let's just ignore the turns ratio. I don't want to make my life more complicated. Okay. Lastly, we could talk about the impedance of the transformer. This is where it gets really confusing. Okay, so how can we make the impedance calculations easier? Well, again, ignore turns ratio. Okay, now what's the turns ratio of converting impedance from one side to the other? It's Z1 over Z2 is equal to N1 over N2 squared. You probably hardly ever even use this in your life. Most engineers won't. Okay, but this is if we want to convert the current looking into one side versus the current looking into the other side, because they are different. Okay, so let's calculate the transformer impedance looking from bus 1 into the 12 kV side. So we're looking into the transformer. What is my Z of the transformer? Okay. Now note, this is different from the current impedance looking from the other side. Okay. So let's calculate this side first. I want my Z of the low voltage side is equal to, yeah, I wrote ZT. Let's do LV, right? Z from the low voltage side looking in. So Z low voltage actual is per unit times our base value. Okay, what's my per unit? Well, they gave it to 0.1 right here, or 10%. So 0.1 per unit multiplied by my base value. What's my base value? Rosetta Stone time. 12.5 kV. Let's go up here. 12.5 kV column, Z base, 1.56 ohms. So let's bring it back down here. 1.56. Let's number crunch that. That's going to be 0.16 ohms. So when we're looking in from the low voltage side, this transformer impedance is going to be measured at 0.16 ohms. Now, let's look at the high voltage side. So calculate the transformer impedance looking from bus 2. Oops. So transformer impedance looking from bus 2 into the 12 kV side, 25 kV side. So we're looking at the impedance from the high voltage side, which is going to be drastically different. It's going to be different from N1 over N2 squared. Okay, so we're going to have to look at Z high voltage equals per unit times base value equals, again, our Z percent is 10%, 0.1 per unit. We're going to multiply by base value. What's this base value? Rosetta Stone time again. 25 kV column, Z base row is 6.25 ohms. Okay, 6.25 ohms. 6.25. Let's number crunch that. That's going to be 0.625. I'm going to round it to 23 ohms. Okay, so that's the impedance looking in from the high voltage side. Now, are you already confused? I'm confused. You know, you got, depending which side I'm looking at, the impedance changes drastically, right? Am I looking at the high voltage side, impedance is 0.63. I'm looking at the low voltage side, 0.16. Well, which one do I actually use when I'm doing power calculations? Exactly. It's confusing. No one uses a system of ohms on the high side, low side. Literally, I've never seen it once in the power system, maybe once or twice. But everybody uses 10%. Isn't it just much easier to say, hey, my impedance is just 10%. That's it, right? Look, boom, done right here. I'm not going to say, oh, well, 0.16 from the low side, 0.63 from the high side. No, we're just going to say this transformer impedance is 0.1 per unit and just walk away. Okay, and this is the main beauty of using per units, is we almost ignored all the turns ratio problems of transformers. It got so much to where we almost can just think the transformer's not even there anymore, right? Because the turns ratio is gone, right? So that's one of the biggest advantages of per unit system. And we're going to come back the next class period, and we're going to keep on going and showing you how to use more per unit systems with transformers and with generators and lines and all this other stuff. Okay, so again, thank you for showing up. Hopefully we got a good basic idea of a per unit systems, and we'll see you in the next class period to continue. So you guys have a good day. See you later.